All right, so here is our first example. We have a proton. I'm going to draw it to the side over here. Proton is traveling to the right at 2 × 10⁷ meters per second. It has a head-on, perfectly elastic collision with a carbon atom that is initially at rest. The mass of the carbon atom is 12 times the mass of the proton. We want the speed and direction of each after the collision. All right, so collision momentum is conserved. Our system includes the proton and the carbon atom, the two objects involved in the collision. We can say that M1 V1 initial plus M2 V2 initial needs to equal M1 V1 final plus M2 V2 final. This needs to be true simply because it's a collision. The reason either object changes its motion is because it is interacting with the other object. In this case, the carbon atom is initially at rest, and so we are looking for V1 final and V2 final. We have two unknowns, which means we need another equation. All right, so, well, technically we have 3 unknowns because of the mass, but with this relationship between the mass of the carbon atom and the mass of the proton, the mass part will simplify down nicely. A couple of things here. A head-on collision, meaning it's all along the same line. So after they collide, the carbon atom is going to be moving to the right. The proton will be moving along the same line, and it's actually going to end up bouncing back. And you don't need to recognize that at the moment, but we will show that. So head-on just meaning they don't hit on the edges, so they do not take off with X and Y motion. Perfectly elastic means the kinetic energy right before the collision in the system as a whole still has to be kinetic energy after the collision. Final. And I'm not sure why I wrote M2 first, but in either case. So again, the carbon atom is at rest, so we have 2 equations and 2 unknowns. The equation that describes the conservation of momentum in this situation, and the equation that describes the conservation of energy, kinetic energy specifically. Now, we could technically solve this, but if you happen to remember, in the test notes, oh, this isn't working like I thought it would, but here we go. Solving the system of equations for an elastic collision for 2 particles moving only in one direction. The first starting at velocity V1 initial, the other one at rest. These resulting equations come from substituting for V1 or V2 final into so solving for either V1 final or V2 final and putting it in the other, these resulting equations are what will come out. Meaning we do not need to do that math, the substitution ourselves. But it's specifically because this is linear motion, because one of the objects is at rest, and because this is specifically an elastic collision. So I'm just writing these equations down. So V1 final, 1 means our proton. So this is going to be the proton's final V. M1 is the mass of the proton. M2 is the mass of the carbon atom, but the problem told us that the carbon atom is 12 times the mass of the proton. So I'm putting in 12 times the mass of the proton in place of that. And V1 initial is that 2 times 10 to the 7th meters per second. So in the numerator, we get negative 11 mass of the proton. This is without the speed, so just looking at the mass portion. In the denominator, we get 13 times the mass of the proton. And so, as I was mentioning before, the mass of the proton itself will cancel out once we have made that substitution. So plugging this in, I'm not going to count my decimal places. Let me change my mode. So negative 1.69, 2 times 10 to the 7th. Okay, so what this means is the proton is traveling to the left, opposite the direction it was moving. In the problem, it said it was moving to the right initially. The negative sign means it's traveling to the left, and it's traveling essentially with the same speed, or 1.7 times 10 to the 7th meters per second. So it's not going as fast, but it's also completely headed in the opposite direction. Now left, simply because the numerator in our equation for V1 final, if the object or particle, essentially, the second object that starts at rest, if it's more massive than the first object will always bounce off and head back opposite its original direction. For the carbon atom, this numerator, is M1, not M initial. So mass 1 is the proton. In the denominator, mass of the proton, 12 times mass of the proton. And then we multiply that by the initial velocity. So the numerator gives us 2 mass of the proton, the denominator gives us 13 mass of the proton. The mass of the proton cancels again. And I'm getting 3.1 times 10 to the 6th meters per second. The fact that we're getting a positive answer means the carbon atom is headed to the right. It's headed in the direction the proton was traveling in originally, which hopefully makes sense. If you get hit behind, you end up moving forward. So that's what this is essentially showing us. It's not traveling nearly as fast as the proton was, though, because it is so much more massive. So conservation of momentum, in this case, perfectly elastic. We could use those equations. Keep in mind, these equations are specific to perfectly elastic. The whole problem has to be linear. So everything, all the motion has to take place along a straight line, and the second object has to be at rest initially.